So 1 minute to start. So let's get started. My name is Denis, and today we'll talk about simplicity. You know, usually simplicity is not what we're thinking of when we hear about Haskell. But give me a chance to prove you that Haskell can be really simple. Because we're going to talk about simplicity, so my talk will be really simple. So even if you know absolutely nothing about Haskell, trust me, you'll understand all examples. So what is simplicity? You know, the man who said these words wasn't a software developer. But I totally agree with it, because this is the reason why novices tend to create too complex solutions. But when we become more and more experienced, we are striving to simplicity. That's true. And when we are talking about maintainability, actually we are talking about simplicity. It's simplicity of how easy we can fix our code, refactor our code, or improve our code. But actually the one key idea about simplicity is how easy we can understand our code. Because actually we cannot fix or improve our code if we don't understand it. And the problem is that we are talking about the code, but actually today we don't write the code. You know, the code, it's something about assembler or probably C. But today in modern languages we don't write the code. We write the letter. And the problem is this is the letter for computer and for human in the same time. This is trade-off. And I'm going to show you 3 simple examples about simplicity. Very practical, very easy to understand examples. So it's about messages, it's about missiles, and it's about pages. Please raise a hand if you work with frontend. The third example is for you guys. And 3 main tools we use for achieving this simplicity is types, purity, and pattern matching. So let's get started with our example. So many years ago in one project we worked with messages. What is a message? It's a very simple idea, message. So how can we express this idea in our code? Of course with some type. Message. So this is example in C++. Very trivial example. This is our expression that we think about message, and this is our code for message. This is message with text inside. And this is how it looks like in Haskell. It's the same type, trust me. Just a message with text inside, nothing more. We don't need anything more than in this example. And time changed, and after some changes we decided, no, we cannot send message like a pure text. We must encrypt it before sending. And business logic tells us that we cannot send message in unencrypted view. We want to have guarantee that probably code that will try to send message in unencrypted view, we don't want it work. So probably, okay, this is how we can extend our C++ type. We just add some state, Boolean state, and checkers. Is it encrypted? It's very simple. And two methods, encrypt, decrypt. It's really trivial. So how can we, but actually we don't need any state here, because all we need, data message is equal to plain text or encrypted text. There is no state. There's two variants of the same type, and we just have two functions, encrypt, decrypt. It just works with message.
Where is the keys?
Good questions. So, and this is how we can use this type. Just plain high Minsk and just encrypt it and send in encrypted view. And probably, if we already have encrypted text in some file, we just read this file, put it in our encrypted box, and send it. And okay, let's talk about how can be implemented send function in C++. We just have message, recipient, and we have to check. Is encrypted? If so, just give us this actual text and send. If not, just throw an exception. So a trivial example. And how can we do the same thing in Haskell? That's it. It's something strange. We have type of this function and two bodies. Actually, there is one body, but pattern matching, we just match if this is encrypted text. Okay, just put this text via pattern matching and send it. If not, if we see that this is plain, do you see these underscores? We just think, no, we don't care what in this message. We cannot send this because it's plain. So just throw some exception. So is this a good example? No, it's not. It's a very poor example because all we did was just port some C++ code into Haskell. It's relatively good, but we don't want this pattern matching by plain encrypted. We want to get some guarantees. Business logic tells us we cannot send an encrypted message. And what we really want is that if we have a code that will try to send plain message, this code shouldn't be compiled. So let's do it. This is a new version, simpler version of our message type. And in this case, data message, some state is equal message text. Wait a minute. So we can some state in left side, but we don't use it in the right side. This is a phantom type. Phantom type is really phantom. It exists, but at the same time, it doesn't exist because it exists only in compile time. And we provide two dummy types for states, plain and encrypted. And we cannot create values of plain or encrypted types because these types are not for values. These types are for guarantees. And take a look at these functions, encrypt, decrypt. Now we can express directly on types level that encrypt take plain message, not some message, but plain message, and returns encrypted one, and decrypt vice versa. So in this case, we can easily think about this code. And what we now look, we see in send function, there is no pattern matching with encrypted and unencrypted. We just define that first argument message encrypted. So if we'll try to put message plain in this example, it doesn't compile. And if we see that our code compiled successfully, we definitely know that we send encrypted message. It's guarantee from our compiler. Moreover, suppose we, encrypted, plain. What if we want to add some third state? For example, in base 64, it's some third state because we want to take some binary message and put it in plain text view, some printable view. And in this case, we can, these two examples. First of all, we can define functional message length, and we talk that message state, with any state, it will compiles because we probably want to get a length of different messages. Plain message, encrypted message, it's binary, but we can take its length. But function to base 64, we take again some message state and returns message in base 64. We know that this function cannot return us message in any other view, in any other form. So if this is successfully compiled code, we definitely know about it. Okay, let's move on to our second example. What about missiles? Before we look at the missiles, this is an example from one real project, calculator of food for diabetics. So we take some food info and we return some results. So the question is, what can we say about this function? How it works? We cannot say anything about how it works. Actually, it's a black box. How it calculates? Probably it's reads some file, goes into database, etc. We cannot reason about this function if we are looking for this declaration only. This is the same function in Haskell. And if we know what types are food info, food, and result, we can be sure that this function cannot contain any danger surprises for us. Why? Because this function is pure. What is a pure function? This function doesn't have any side effects. Its value depends only these two arguments, and this function cannot work with external world, external danger university. We can be sure because Haskell provides us guarantees about purity of function. But if we do something like this, in this case the weather is worse because we see I/O. I/O is a big black hole, and if we have I/O, this function tells us, well, I can work with danger university, with files, with inputs, with database, so be careful with me. But I know what can we think about it. What's the problem? This is C++ and this is a pure function. It just calculates degree value, and if we call this function 1,000 times with the same degree, we get the same result. That's true. So can we say that this function is pure? No. Why? Because of this. Because we can launch missiles in it. And the problem is that declaration of this function didn't change. But its behavior, it's really changed. Or for example, this variant. So if we call this function 2 times with the same degree, we cannot be sure that the result will be the same, right? Because if we're talking about pure function is not a function without side effects. Pure function is the function that cannot have side effects. It's impossible. So it's when we look at this function, it's not about our beliefs. We definitely know that this function cannot, for example, corrupt our database, because it cannot work with database. It's impossible. And it doesn't matter how long, how big this function. We can just see its type, its declaration. And if we know what the types are, food info, food, and result, we definitely know that this function is able to do something and unable to do something else. Okay, so let's move on in front-end world. This is CSS, written directly in Haskell. with Haskell DSL. And if this code compiles successfully, we definitely know that CSS that will be generated by this code will be valid. So we know it. So this is a style for by form for one payment service in internet. And this is HTML written in Haskell. Another example. And if this code compiles successfully, we definitely know that our markup is valid. But there is one problem. Third line. Do you see it? A dot. Just copy paste. By form. I shouldn't use dot in markup, because it was copied from this. So it compiles correctly, but actually it doesn't work. So how can we fix it? Because actually we don't want just correct CSS and just correct HTML. We want that they work together. Let's do it. So how can we fix this example? Let's create a type, class name. This type includes all CSS class names, including by form. It's just the values, just the null reconstructors. Just by form, it's not a number, it's not a flag, it's just by form. And this line is a black magic. Please remember it and you will see how it works. We changed our CSS declaration. So now we don't have any string with dot. Why? Because this by form value of that type class name can be converted in string automatically. And we just append this dot, and it works. And how can we use it in our markup? Now we just use by form a function to value, just take this value and convert it to the same string. So in this case, if this code is compiled successfully, we can be sure that not just it's correct HTML and correct CSS, but these styles and markup are work together. It's guaranteed. Because if we have a lot of classes, so we can just rename some class in one place and forget to rename it in other place. But in this case, it's impossible because it won't compile. So these three simple tools, simple mechanisms, types, purity, and pattern matching, these tools can help us to simplify our code because we can work with code not just simply, we can reason about it. And our compiler is our friend because if it just kick our heads, so no, it doesn't work. So if we can see that code is compiled successfully, we definitely know not in all cases, because we can see Haskell code which is compiled but doesn't work properly. Okay, it's possible. But in many cases, compiler will check a lot of not all errors, but a lot of errors. So we can be sure that these errors is impossible is our code. Thanks. Your questions.
Talking about your first example, talking about types, you have demonstrated a case when you convert exception into a type check and construct. But I think that there are some cases when you get your data not from your own program. You cannot express it as a type because you can get it from external API. System. And how do you suggest to deal with such cases by using type system? So is there any like mappings or some Haskell approaches to convert some data of format which you don't know, or you have missing field, missing attribute, and with help of type system?
So actually in our code, of course, we use exceptions. Yes, we use exceptions because in some cases we just cannot reason about the data because external world is out of control. And we just take it, for example, parse it, and we cannot be sure. In this case, unfortunately, we cannot be sure what is the text that we read from some file. So in this case, we must check these, for example, via pattern matching and probably deal with exceptions. So there's no problems with it. But my example is not for all cases, of course, because if it would be for all cases, it's really great. It's ideal life. But of course, if we read some database value, we cannot be sure. So this value is valid. So in this case, we can, okay, let's check it in some case, and probably it will, or some exception or optional value. For example, if we don't show that this value is what we expect. Another questions?
Maybe in that purity example, it should be noted that they may be seemingly pure functions, but they are using unsafe, perform whatever under the hood, and that is breaking those speech. And on the other hand, it can be also noted that there is a special Haskell extension, safe Haskell, to ban such things.
We actually have some, okay, I have to reveal some secret. Okay, that's a great question. If we see this declaration, we can be sure in almost all cases. Because there is a way how we can put impure side effects in this function. But first, this is a very, 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 very bad practice. Very bad practice. And the good news about it that we can compile our project in special safe mode for GHC compiler, and in this case, compiler will show that you try to put some, for example, we try to put some code that writes information in file in this function, and it's really, really bad. Really bad. So just forget about this ability. So it doesn't exist. Just forget about it. But even if some developer did this bad thing, compiler can check it. And in this case, our project doesn't compile at all. And it will show where this unsafe code exists.
Thank you for the presentation. You told us about, you mentioned that we should remember drive show, but I didn't get where you did show it.
Drive show?
Yeah. There was a string, you told to remember this thing. I'll show it this magic later.
Okay. This is derive and show. It means that we tell to compiler, dear compiler, please take the any value of these types and convert it in string as it is. So in this case, by form, big letter, and in this case, just by form. Because without that derive and show line, it's impossible.
Thank you. So it was lazy initialization of the answer.
Yeah.
Could you please show your two-base 64 function?
Wait, sorry.
Yeah. So this function can take a message already encoded in base 64.
Yeah.
And you can apply it multiple times, and in words you lose the information. How many times you already encoded?
Really great question, because when I wrote this example, I think probably someone can ask about this, because message state, this is for simplicity, but in a real project we can think so this function can, we don't want that this function can take already encoded text, so we can rewrite this example. So it will be impossible to put in base 64 again in this function. But this example just short because we can just small display.
Actually, I have just a comment. It's a bad joke. You're talking about simplicity, but the funny thing that normal programmers do not start programming with introducing a class message. They would just use a string.
But this is a bad practice because string is not a message. It's just a string without any sense. Message is not a string, and string is not a message. When we want to express our idea in code, so string is not a message. But message is a message. So? There's no more questions.
Okay, thank you, Denis. I think that we will have a break for lunch. And